Now here we have a fun idea that we want to impact. It's one of my favorite things about this doppelganger mathematical journey. And what it is about understanding how quickly things change. What's its slope? And with squiggly lines, we can't find its slope because the line is squiggly. If it was straight, we can. So what do we do when we have a squiggly? Well, we start to learn a little bit about calculus. And what calculus is telling us to do is let's look at its average rate of change between two pieces of the graph. So for example, if I chose a point here and a point there, and I connected those points with a line, that line will show me or give me the average rate of change between those two values. And this model that we have up here, f of x2 minus f of x1 over x2 minus x1, will show us what the average rate of change is. Now, did you notice what that looks like? Looks a lot like the slope model, doesn't it? The slope equation, y2 minus y1 over x2 minus x1. Yes, that's basically what we have. We're looking at the slope between 2 points in a function, and hence the designation of f's rather than y's in that particular model. So what we're going to do is, well, what's the slope of that line within that given distance? So let's look at an example here to see how we can look at that. A common function that we're going to become real friends with is x squared. Now, the graph of x squared goes through the point 0, 0, 1, 1, and 2, 4. It's an even function, so it parallels on the other side, or it mirrors on the other side. And so let me try to almost hit those dots the way I wanted to. So there's a graph of x squared. Yes, it's an even graph. It's symmetrical about the y-axis. And so what we want to find out is, well, what's its average rate of change? Well, you can see that the average rate of change, it's decreasing quickly and then it's changing, and so I can't tell. So what we have to do is we have to look at it over intervals. So let's look at it over the interval between 0 and 1. What's its average rate of change doing? Basically, between these 2 points, what is its slope there? Well, I have 2 points that are given. I know that this point right here is a point 1 and 1, and this point, the origin. So let's solve that in this equation. That becomes f of x2 is 1 minus x2 over f of x1 minus, or sorry, f of x2 minus f of x1 over x2 minus x1. Whew! That equals 1. So the average rate of change, its slope between the first 2 points I marked, is 1. All right, now let's look at it on the interval between 1 and 2. What is its average rate of change? Basically, we're looking at these 2 points. There, its average rate of change. Again, let's look at the model. It's 4 take away 1 over 2 take away 1, which gives me a 3/2. So its average rate of change is, sorry, 3/2. Yeah, wait a minute. 2 minus 1 is 1. Back up. Its average rate of change is 3. So I went from a slope of 1 to a slope of 3 by looking at a different interval of the line. Now, I want to look at one more interval. I want to look at the interval from -2 to 0. What's happening on that interval? I did not intersect the origin there at all. So let's make it big like that so I can't. So we can look at that. The slope of that line, it would be a -2 minus 0. Or sorry, that's -4 up there. -4 minus 0, and it has a run of -2 minus 0. which equals negative 4 over negative. Sorry, positive 4. 4 take away 0 is positive. The x-axis is negative. Negative 2 minus 0 gives me a negative 2. So I have a slope on that interval of negative 2. So when we're looking at the average rate of change with squigglies, we're going to have to look at it at specific parts of the graph over certain intervals. And then over that segmented interval, are we able to determine what its average rate of change? If we looked at the entire graph, its average rate of change will always be changing. It'll be hard to determine with our skill set right now. But one day, we're going to be able to do this. Every one of us will be able to do its average rate of change over the entire graph.